Okay, welcome to the next video in this series of screencast lectures for Math 1410 Linear Algebra. So we're going to continue on now with our study of equations of planes in 3 dimensions, and we're going to look at how do you actually determine the equation of a plane. So one of the things that you'll recall is that if you, so just as a reminder before we begin this example, is that if you're given a normal vector n equal to a, b, c, and a point, let's say x naught, y naught, z naught, then you get the equation. You get this equation for a plane. So the equation for your plane is going to be n dotted with this vector x minus x naught, y minus y naught, z minus z naught equals 0, right? But if you expand out the dot product, what that dot product looks like, you got a times x minus x naught plus b times y minus y naught plus c times z minus z naught. And notice in particular that you have a times x, b times y, c times z. So the components of the normal vector, they show up as the coefficients of x, y, and z in the equation of the plane. So with that in mind, coming to an example like this one, where instead of being given the normal vector and a point, which is kind of the simplest scenario that you might find yourself in where you're trying to write down the equation of a plane, here we're given a point that is on the plane, and instead of being given the normal vector, we're given a parallel plane, right? So maybe the plane we want is here, and we're given the equation of another plane up here, which is parallel, right? But parallel means the normal vectors for those two planes should also be parallel. So in particular, if they have the same normal vector, they're going to be parallel planes. So what we can do is we can determine the normal vector for the plane that we're given, and we can use it as the normal vector for the plane that we want. And so we look here and we see 5x minus 3y, don't forget the minus sign, the 2z, and we compare with the sort of generic equation that we have here, and we say, well, given this equation, 5x minus 3y plus 2z, we compare with the general scenario, and we say, okay, so a here must be 5, right? So this a must be our 5, the b must be our minus 3, the c must be 2. And so we can now identify that for our given plane, so for the plane with the equation 5x minus 3y plus 2z equals 0, we have the normal vector 5 minus 3, 2. So we can go ahead and use that normal vector to compute the equation for our new plane. So the only thing that we're going to do is we're going to change the point, right? So I don't know what point was used to determine that original equation, but we're going to use this different point here to get the equation for our new plane. So how do we do it? Well, we follow this procedure here in the reminder, and we say, all right, the equation for our new plane, it must have the equation. Well, it must be n dotted with x minus 7, y minus 1, z minus 3 equals 0, putting in the equations for this point p naught. And so what does that give us if we actually write things out? That tells me that 5 times x minus 7 minus 3 times y minus 1 plus 2 times z minus 3 equals 0. Okay, and then there's nothing wrong with leaving your equation like that. If you want to simplify, you can, but there's nothing wrong with leaving it in that form. If we want to do one more step, we might say, okay, so our equation is 5x minus 3y plus 2z is equal to, what are we going to get here? 35 minus 3 plus 6, so 38. Okay, so notice that the left-hand side is the same as it was for the parallel plane. what changes is the right-hand side. So the point on the plane affects that value that you get on the right-hand side. So we see that showing up here. Okay. So moving along, I'll also remind you that last time we said, well, one of the other ways that you can write down, describe a plane is by giving a pair of vectors. So we said, if you have two vectors, right? So this is, like v, and this is say w here, right? This is another way that we can describe a plane because, our picture again, remember, is that we start with our sort of point somewhere in space. Here's our point corresponding to this. This is the vector for sort of p naught here, right? So here's our point p naught. And then at that point, we've got our vectors, say, v and w through that point. And then the plane is sort of everywhere that you can reach by traveling in some combination of the direction of v, going some distance in the direction of v, and then some distance in the direction of w from the point p naught gets you to anywhere else on the plane. So that's what this equation is describing. So this is fine, and this is certainly one way that you can describe a plane, but it's not as convenient as the scalar equation, right? This equation is a little bit bulkier, so how do you clean it up? Well, to clean it up, we need a normal vector. So how do we get a normal vector? Well, the normal vector should be orthogonal to every vector in the plane. In particular, that normal vector should be orthogonal to both v and w. But we know how to construct a vector which is orthogonal to two given vectors. That's simply the cross product. So we calculate the cross product, v cross w. So this is going to be what? This is going to be, let's write things out, I, j, k, 1, 0, minus 2, 0, 2, 1. And let's work things out. We're going to get for I, right? So I'm doing, for the I component, I'm doing this guy here. I get 0. 0 times 1 is 0. Minus 4. 0 subtract minus 4 gives me the plus 4. So let me just get that out of the way. Let's erase that. Right, and then for j, remember we put the minus sign in front of the j. We do, for j, we're going to do 1 times 1, and then we subtract off, well, minus 2 times 0. Well, that's 0, so j, we just get minus 1. So minus 1 times j, minus 1 times j. And then for k, we're going to do 1 times 2, subtract 0 times 0, so that's simply 2 plus 2k. So that's the vector 4, minus 1, and 2. Remember, if you want to make sure that you didn't make a mistake, you can calculate the dot product of this vector with the two vectors you started with. Make sure that you do indeed get 0 for both of them, and you can check quickly that that is the case. Now that you have the normal vector, well, you already have a point on the line. It's this guy. So now that you have a normal vector and a point, you can get the scalar equation. The scalar equation is going to be, given by, well, the normal vector dotted with, I think we called that r before. So let's do that again. R minus r naught equals 0. So that comes out to, well, 4 minus 1, 2, dotted with x minus 3, y minus minus 2, so y plus 2, z minus 4. That should be equal to 0, so this gives me 4 times x minus 3 minus 1 times y plus 2 plus 2 times z minus 4 equals 0, so this gives me 4x minus y plus 2z is equal to, let me see, it's going to be 12 plus 2 plus 8, that's 22. Okay. All right, let's try another example. What if we wanted to go in the other direction? What if we wanted to take something given in scalar form and we wanted to write it in vector form? So one of the things we can do here, well, the first thing we need is what's our r naught? We need our point, right? We need a point. One of the ways that you can choose a point, and any point will do, is that if you put y equals 0 and z equals 0, what does that leave you with? That leaves you with 3x equals 6, so x is equal to 2. So that means that you can take the point 2, 0, 0, and that's on the plane. Okay. Generally, if you set two of the three variables equal to 0, then you can solve for the remaining variable and figure out a point. So here we set y and z equal to 0 and solve for x. We could have also set say x and y equal to 0 and got z equal to 3. That would work too, but this is the one we chose to do. Now, what do you do with the rest of it? So what you can do is you can say, all right, let's rewrite this equation here as, let's see, the thing that's easy to solve for here is y, right? Y is equal to 3x plus 2z minus 6. And actually, we can probably skip the step of choosing the point, right? Let's actually, let's leave this out for now, okay? We'll see that we don't need to do it. We can do everything all at once. How do we do it? Well, once we've got y in terms of x and z, right, then x, y, z, okay, I'm going to write that as, well, x, and then 3x plus 2z minus 6, and then z, okay. Now, I'm going to start sort of pulling things apart here. I'm going to break this into three vectors. X, 3x, 0, and then 0, 2z, z, and then 0, minus 6, 0. Okay? So all I've done is in the first vector I had all the things that involve x, right? So the x here and the 3x go into this guy. In the second vector I've got all the things that involve z, and in the third vector I have any constants. There's only one. It's the minus 6. Okay? So now what I can do, so the point p naught I'm going to take, it's going to be this guy. This is going to be my p naught. 0, minus 6, 0, right? We can check that that's also a point on the plane. If x and z are both equal to 0, y has to be minus 6. Now I'm going to do one more step here. I can take the x out from this guy, 1, 3, 0. You can take the z out from this guy, 0, 2, 1. And then 0, minus 6, 0. And so this first vector here, right, this is going to be like my v. This guy is going to be my w, right? I'm using x and z instead of s and t, but you'll notice I still have this form here, right? So, and then this is my r naught here, right? Here is my r. And so I've got things into that same form that we saw on the previous slide. R equals r naught plus s times v plus t times w. We've got it in that form. We just have to set x equal to s, z equal to t, and we've got it. Okay, moving right along. What about the equation of a plane containing 3 points? So for this one, we're going to have to, well, let's draw a diagram. Actually, let's not even bother to put axes in. P, Q, R, okay? So we've got 3 points that we know are in our plane. Well, once we have those 3 points, we can draw 2 vectors, right? We can say here's V, here's W. What are V and W? V is going to be the vector, well, I do head minus tail for the vector PQ, so coordinates for Q minus coordinates for P, minus 2 subtract 0, 3 minus 1, 5 minus 2, I get minus 2, 2, 3. W is going to be equal to, so I do coordinates of the head here are R, tail is P, so I do 1 minus 0 is 1, 1 minus 1 is 0, minus 3 subtract 2, I get minus 5. Okay, so now that we've got those 2 vectors, well, we can compute the cross product, and actually we're going to have to pause this momentarily. I will come back to this, but you're going to see a little interruption here. As we pause this, we're going to return with the rest. Okay, and we're back. Sorry for the interruption. All right, so let's continue with this example. We're trying to find the equation of a plane containing these 3 points. So far what we've done is we've found the vectors. So we found this vector v, so this is the vector from P to Q. We found this vector w, which is the vector from P to R. I've chosen to draw both vectors anchored at the same point P. You can set this up however you want, right? Any two vectors will do as long as they're not parallel vectors. So you could do the vector from P to Q and the vector from Q to R. It doesn't matter as long as you get 2 points or 2 vectors which are parallel to the plane, right? And so any vector between any 2 points in the plane will be parallel to the plane. You might think that it matters. It seems like, if you did say the vector from Q to R, you get something which is completely different from the 2 that are already there, and it seems like, this should make a difference. If you're concerned, feel free to try this. Try it a couple different ways. See what happens if you choose different vectors, and you'll find that you end up with the same equation every time. And then you might want to think about why do you end up with the same equation every time. You can play around with these sorts of things. A lot of them can be understood if you kind of carefully study the properties of the cross product. And speaking of the cross product, that's what we need to find next, right? Because the normal vector, we know that the normal vector is going to be the cross product v cross w. So I, j, k, minus 2, 2, 3, 1, 0, minus 5. Okay, so for the I component, we just have 2 times minus 5, and then it's 3 times 0. So that's minus 10 subtract 0, minus 10i. For the j component, minus 2 times minus 5, that's plus 10, and then minus 3. So we're doing 10 minus 3. So remember that minus sign for the j component, and then 10 minus 3 gives me 7j. And then for the k component, we're doing, well, that's 0, right? And then we're subtracting 2. So minus 2 times k. So our vector is minus 10, minus 7, minus 2. By the way, if you don't like all those minus signs, you can switch them, right? Any vector which is parallel to the normal vector will do. So if you want to use, you can use, we could say, let's actually say this is not what I want for my normal vector. I'm going to use the normal vector 10, 7, 2, because that's parallel. It's still going to work. So now that we got our normal vector, we can choose any one of the 3 points that we were given to begin with. I'm going to go with P. I've kind of anchored everything at P, and we can write down the equation of our plane. So our equation is going to be 10, 7, 2 dotted with, so x minus 0, y minus 1, z minus 2. That should be equal to 0. If we clean this up, we've got 10x plus 7y plus 2z equals, what are we going to get? There's a minus 7 equals 11, if you simplify that. Okay, good. So one more example on this video, and then we'll move on to the next one. So the last example we're going to do, equation of a plane containing intersecting lines. All right. Now notice we decided to be nice here. We chose 2 lines that are obviously intersecting, right? We've got that same point on both lines. Otherwise, you might have to first check to see, do these lines actually intersect? Because if they don't intersect, they don't lie in a common plane. And well, then you've got some work to do. By the way, if you want to give yourself a little bit of a challenge, think about how you would write down the equation of a plane containing parallel lines. We could work on that one as well. Maybe ask me to do that one in class. If we have time, we'll do that as an example. All right. So we've got our 2 lines. We've got the equations for the 2 lines. How do we get the equation for our plane? So, well, we've got line 1, we've got line 2, we've got a point of intersection. So we might as well take that point of intersection to be our reference point on the plane. That's just going to be our point 1 minus 2, 0, right? And then we've got direction vectors for the 2 lines, v, w, here is v, here is w. They're just the direction vectors for the lines. And then we know how to calculate the normal vector. From those two lines, we calculate the cross product. So we go ahead and we calculate the cross product. V cross W. So as usual, we'll set this up as a little 3 by 3 array. So we have -2, 3, 1 for the vector V. We've got 3, -4, 2 for the vector W. And we compute this. So for the I component, we've got 3 times 2, that's 6. Subtract -4. 6 subtract -4, that's 6 plus 4. Gives us 10. I. Let's put that minus sign down right away for J so we don't forget it. And what do we have for J? We've got a -4, -3. So -7, so minus 7. So that's going to come out to be a +7. And for K, -2 times -4, that's 8 plus 8, subtracting 3 times 3. 8 minus 9 gives me -1 times K, so minus K. So overall we get 10, 7, and -1 for our normal vector. Now that we've got our normal vector and our point, we know how to write down the equation of the plane. Our equation is going to be 10 times x minus 1 plus 7 times y, subtract -2, so y plus 2, minus 1 times, well, z minus 0, so just minus z, equals to 0. And if we want to simplify that, and again, you don't have to, but you might want to, 10x plus 7y minus z is equal to 10 minus 14, minus 4. Okay, that's it for this video. In the next one, we'll look at some distance problems, finding distance between points and planes.